So we're going to be learning about how diodes work. So first of all, what is a diode? Well, a diode, the electronic diagram circuit symbol thingy for a diode looks something like this. That's what it looks like. And the diagram is supposed to conveniently represent what it's supposed to do. And that is, namely, so if we think about conventional current, that is the flow of holes, i.e. the absence of electrons, then a diode is supposed to let current flow, conventional current flow this way, as indicated by like this arrow looking kind of bit, and it should stop current from flowing this direction, and stop is indicated by this wall, do not pass kind of thing. And just to sort of reiterate what I mean here, let's say we have some battery like this. This small end of the battery refers to the negative terminal. This big long bit refers to the positive end of the positive terminal of the battery. And okay, let's say that this was just a normal circuit with just, some resistor here, some load here, right? What usually would happen in this sort of circuit is conventional current will want to flow from positive terminal of the battery to the negative terminal around the circuit like this. That's what usually would happen. But of course, in reality, what's happening when I draw this diagram, this arrow here, is really what's happening in reality is that electrons are going to be going this direction. They're going to be attracted to the positive end of the terminal. The positive terminal of the battery. That's what's really happening. Electrons are the thing that's moving, but we can model an positive charge moving around in the opposite direction, and we can model it like this, and that works out the same way. Even though this is not a real thing, this is like the absence of electrons, right? This is positive holes. When we say conventional current, that's what we mean. We're thinking about holes, i.e. positive charges moving around the current like this, from positive to negative. And the reason why this happens as well, you can think of it like this. Positive charges are, the wire initially has like positive and negative charges everywhere, sort of like uniformly distributed. These positive charges, they're going to be repelled from the battery as soon as we put it in the battery. So these positive charges are going to be repelled from this, and they're going to be attracted to the negative here. So it's going to go like this. And this is going to be some positive, and this is going to be negative. And this difference is what draws it to go there. So I mean, for example, if this was really negative and this was a bit positive, then it would make sense that electrons would be positive charges, our imaginary positive charges. It would make sense that these would be more willing to go over to this side, So that's how circuits usually work. Just a quick, recap. Now let's go back to our diode. All right, I moved the diode up a bit. So how is this actually made? Well, it turns out it's actually quite simple. What we do is we use semiconductors. So it turns out that what we have to do is we get some p-type doped semiconductor, and we put it right next to some n-type doped semiconductor like this. And so why does this behave like a diode? Like, why does it block current in one direction and allow current from another direction? That's what we're trying to understand. And I'll explain what this means in a bit. But just a quick note, the p-type section of the diode is called the anode, and the n-type section, wait, maybe I'll do this in a different color. What is that? That's very strange. So the p-type bit is called the anode, and the n-type bit is called the cathode. So what p-type means is that what p-type doped silicon means is that we have some silicon, and we have doped it in such a way that we have a lot of free positive charges. Again, obviously this is not a real thing, this is the absence of electrons, but we model it as positive particles, sort of, that can flow around in here freely. Where doping just means that we've introduced some impurities to the, silicon or whatever semiconductor we have there, such that this happens. And I won't go into detail about how you do this, but I can do later. But that's not the focus of this video, right? Just trust me that you can make this happen using some funky techniques. And n-type, similar deal, but it means that we have chemically altered the semiconductor in such a way, we've doped it in such a way that we have a lot of free electrons, free negative charges that can kind of just flow around. And this is where the names come from as well. So the p-type refers to how we have these positive particles that can flow around, these positive holes that can flow around, and n-type refers to how we have these negative particles that can flow around freely in the section. Now, let's think what would happen if we plug this in into a circuit. So let's say we connected it to some battery like this, and now, so the symbol for the circuit diagram symbol for a battery is also sort of intuitive. This small bit means the negative terminal, and this long bit means the positive terminal is on this side. And I'll be considering conventional current, so I'll be thinking about positive holes like moving around. And yes, so like I said here in like my little diagram, typically this is what would happen if we had a resistor. If we had just a standard circuit, some load here, let's say a resistor, this is what we would expect to happen. Positive charges moving around like this because they want to get to the negative side, and positive charges are repelled by positive charge here. They're going to go like that. But let's think about what happens here. So this positive charge obviously wants to do this, but notice that we have a bunch of negative charges here. They're going to be attracted to this end of the terminal. They're going to be attracted to this terminal of the battery. So what ends up happening is this. What ends up happening is that these negatively charged bits are going to be attracted to the positive end of the terminal, and so they're going to sort of go this way. And of course, this means that since there's negatively charged bits concentrating here, or like these are, negatively charged bits have moved this way, naturally this means that this end of this section here is going to be slightly more positively charged. And likewise, these positive charges are attracted to this terminal, so it makes sense that this bit is going to be a bit more negatively charged. Now let's consider the flow of some positive charge. Well, it wants to do this. It wants to come around like this, but notice that there's some positive charge there. And of course, positive charges repel each other, so really there's sort of like a barrier here. And you can sort of think of it as like this section here being sort of like a barrier. You can think of that as being like a barrier. And this region is called the depletion region. That is where the electrons have been depleted because it's moved over this way. So, like I say, these positive charges want to go here, and they'll be more attracted to this side. But there's not going to be a flow of current. It's just going to be like a shifting of this bit, but there's sort of going to be like a barrier here. And the only way this barrier could be overcome is if this is really, really, really negative compared to how positive this is, or this is really, really positive compared to how negative this is. In other words, the potential difference across this battery here, potential difference here, must be very large. It must be so large that this, positive charge can go here. It can overcome the repulsion of this, skip over to here. Well, overcome like the repulsion of over here, skip over to here, where, if it gets to this stage, well, then it's good, right? It's going to be repulsed by these these positive charges here, and it's going to be attracted to this. And so, this is when there would be a current, but this is only if there's a really, really high potential difference across the battery here. And this is called reverse bias. Reverse bias. That's when current doesn't flow because there's sort of like a barrier. Okay, now let's go back to before, but we put in the battery the other way around, like that, I suppose. Okay, yeah, if we put it the other way around like that, then, the long side, like I said, is going to be positive and negative terminals, like so. Let's just flip our little friend here. There we go. Okay, now, of course, in a regular circuit, positive charge wants to flow like this. Yeah, okay, let's think about what this positive charge can do. Well, this positive charge wants to get to this negative terminal like this. It's going to go over here, positive charge here. These positive charges are going to repel each other. So these positive charges want to move over to here. This wants to move here, right? That's what's going to happen. And, likewise, this negative wants to move over here. And this negative wants to be attracted. Well, this negative is attracted to this positive here. So it makes sense that these will sort of swap, and the positive charges are going to move nicely through here because they're going to keep swapping and swapping, and such that, current can flow. So, for example, this will go here, making this positive and this negative, and then this negative and this positive will swap, and so on. So negative moves that way, the positive moves that way, and it's going to be happily attracted to the negative terminal of the battery. And current can quite happily flow in this direction. We're talking about the direction of conventional current, might remember. So it can quite happily flow in this direction, which is precisely what the diagram diagrammatically shows as well. So that's how it works. Oh yeah, and I almost forgot to mention that when current is allowed to flow, as represented by this diagram and everything, when it can flow like this is called forward bias. And that's when current can flow. That's about it.